So, hello again, everyone. For those who have decided to join in live, or those of you who are listening again offline, thanks again for tuning in to this latest episode. I'm delighted today to have Professor Andrew Doherty from the University of Sydney and the ARC Centre of Excellence for Engineered Quantum Systems. So, Andrew, thanks for giving me a bit of your time.
It's a pleasure.
So, you are the Deputy Director now of EQUS, and we have had a few other...
technically I'm the acting Deputy Director of EQUS. There's going to be we're going to have a brand new centre of which I will be the Deputy Director when it starts sometime next year.
Oh, okay, so it hasn't officially transferred.
Doesn't officially exist, yes. It's a notional organisation at this point.
Mm. And we've had a couple of people from EQUS already who have sat down and done the podcast. Before we get sort of more into sort of the more big picture stuff that's going on in Sydney and EQUS in Australia, maybe give us a little bit of history about yourself and history of your research, because if you sort of check out the kind of stuff that you've published, you're a theorist. You know, there's probably not a good word to capture you except quantum theorist. You've sort of worked on a hell of a lot.
Yeah, so someone might accuse me of lack of focus. So so I did my PhD in mid-90s with Dan Walls, who ran a quantum optics, theoretical quantum optics research group at the University of Auckland in New Zealand. And I suppose at that time, there were two big things that people working in quantum optics were interested in. One was Bose-Einstein condensation, which was then a pretty new thing, and the other was quantum computing. And so I suppose I was very interested in everything that was going on in sort of quantum physics and quantum computing and trying to manipulate individual quantum systems in the laboratory at that time. And I worked quite a lot with Jeff Kimball's experimental group at Caltech, and we were interested in experiments where you could actually look at a single atom moving around and actually measure some property, like, for example, measure the position at the quantum limit. So, so I really got interested in this idea of feedback control of quantum systems. And so that was really what my PhD was about. How can we measure and control individual quantum systems, look at them, resolve their position, for example, to within the width of the ground state of the wave function or some other measure that it's really quantum mechanical, and then do feedback control based on that. And how do you write that down, and how do you connect that, the way that you might describe that in quantum optics theory, which would involve things called master equations. How do you connect that to the way that classical control theorists would think about things, where they might talk to you about Kalman filters and various other sort of ideas from what's called optimal control. So that was my PhD, and I did a postdoc for 4 years at Caltech, where I worked with Hideo Nobuchi's group and John Preskel's group, and also a control theory group, John Doyle, who's a control theorist at Caltech.
Oh, he was actually, Nobuchi-san was here last week, actually, giving a couple of talks. That's with Pete Drummond. So when you got into this, back when you decided to do this during your PhD, did you come at it, I mean, was there at that point sort of the idea that this was going to have technological applications, or was it very much still we're just playing around with physics and we're just looking at the quantum mechanics of these systems to learn more?
So I suppose I've always been more, I mean, the thing that really motivated me at the time was that when you read about early work in quantum mechanics, and particularly things we'd now think of as the foundations of quantum mechanics, Schrödinger talking about his cat, and Heisenberg uncertainty, and the Bohr-Einstein debates and so on. They were, drawing these beautiful pictures of sort of thought experiments of hypothetical apparatus in which you could actually measure individual quantum systems, control individual quantum systems. And what was amazing about the experimental capability at that time, whether it was in ion traps or in an optical cavity QED or other systems, was that you began to actually be able to perform experiments that corresponded to real experiments that corresponded to those thought experiments. So I suppose my motivation was physics. But there was already, I was very lucky the first year of my PhD to spend time at Caltech, and I remember, going to a talk and John Prescott was explaining this ideas of quantum computing, of error correction, and of fault tolerance. And how do you do fault tolerant gates and things like this. I don't know if I understood all that much about it at the time, but I suppose that definitely already in the field was the idea that there would be certain kinds of technological applications. So that, I think that's always been part of the motivation. And I suppose getting interested in feedback control, that's really sort of beginning to think about an engineering point of view about some of these things. And how do I engineer with quantum mechanics was definitely something people were thinking about.
So did you shift more so that essentially after you finished your postdoc in Caltech, did you then sort of become part of this group who sort of shifted into sort of the more quantum computing and the more technological aspects, or did you sort of just a bit more tepid into it? And
so I think I was pretty tepid when I was in Brisbane. I suppose if you look at my research, there's some of these themes about feedback control we're continuing. Some of these themes about working directly with experimental groups is something I actually really enjoy. So at this point, I've worked with people who are doing controlling single electrons in semiconductor devices, people doing quantum optics in circuit QED devices, people doing optomechanics. So that's something that I really enjoy doing. But you will struggle to find things that are, until recent years, there's not a lot of specifically quantum computing experiments in there. Likewise, I haven't really worked on error correction, fault tolerance, and so on all that much, particularly in that period when I first went to Brisbane. So I would say I was sort of interested in slightly different things in some ways. Quantum mechanics more generally than just quantum computing.
Right. So, I mean, when I was back in Australia, the EQUS, the Centre for Engineered Quantum Systems, didn't exist at this point. There was essentially the Centre for Quantum Computing and the old Centre for Atom Optics. And then the Centre for Quantum Computing, after I left Australia, sort of split, and a large number of you guys at Sydney and the Brisbane folks went on to develop EQUS, and the CQCT evolved into the CQC squared T, or whatever they're going to call the third version of it.
It's going to be the same. It's
going to be the same. So if you could, I mean, for people who don't really know the difference when you're talking about quantum, and we won't even go into the two new quantum centers that have just been funded, but where would you see the delineation between sort of the work that's being done in the CQCT and the work that's more focused at EQUS?
Yeah, so just to give people some context, I mean, so this reference to centres is just reference to a major Australian government grant scheme, and we've been very lucky in the field in Australia. The government's really supported our research across a wide range of research interests in quantum physics. And so these two centres that have existed for a while and have just been refunded that are most closely related to quantum physics. One of them is a centre that really focuses on quantum computing and quantum communication. So that's the CQCT that you're referring to. So at the Centre for Engineered Quantum Systems, I suppose there's two aspects. We are most interested in trying to develop techniques that would allow us to build future quantum technologies that really we're not focusing on quantum computing or quantum communication. So we're interested in applications in metrology, in sensing, maybe in analog simulations of physical systems, but not the focus of our center is firstly to try and develop general approaches to engineering quantum systems. So work like the things Mike Biersick might have told you about overcoming noise in using dynamical decoupling kinds of techniques that you could apply to a wide range of quantum systems to make them behave more coherently for applications that could be just about anywhere you need a qubit. And so we sort of felt that this field of quantum technologies is wide and deep, and we wanted to have research across the range, because it's not really clear, what's the right material system. So in our center, you'll find there's circuit QED, there's optomechanics, there's photonic single photon experiments, there's semiconductor experiments. So we pretty much tried, there's NV diamond work. So we pretty much tried to cover the range of systems where people have demonstrated really convincing qubits, not exhaustively, but to have broad range of experimental activities. And then to unite that very closely with theoretical activities that we're trying to develop some of these tools for engineering quantum systems in general. So the kinds of things you might have heard about from Mike.
And so in essence, you guys arguably have got a much broader mandate than, say, the CQCT, which is much more focused on this idea of a quantum computer or a quantum communications network.
That's right. So I would say that we're both centers are really interested in quantum technologies and building practical techniques out of practical devices out of quantum computing. But something that EQUS does might be David Riley's work, where he's working on hyperpolarizing hyperpolarizing carbon in nanodiamond, and then using that as a sort of a beacon for possible future applications in magnetic resonance imaging. So using some fancy physics techniques, there's quantum physics there, but actually the application could be in medical imaging. And so that's we sort of felt that there's a wide range of potential applications for quantum technologies, and we wanted to focus on those that weren't directly competing with our friends and colleagues who work mainly on quantum computing.
So I mean, in terms of the stuff that you work on personally, or that you're sort of deeply involved in, I mean, what's the most exciting things in your opinion that that EQUS is now sort of touching on, either theoretically or experimentally?
Yeah. So okay. So
what's your state of the art at this point?
State of the art. I'll get nervous because I could make some colleagues happy and other ones I'll miss. There's lots of exciting work going on in the center. Two people that I've worked with closely while EQUS has been there are Warwick Bowen and David Riley. So Warwick Bowen's at UQ. He does opto mechanics research, and I suppose what we've been working on, one of the big questions in that field from a physics point of view is, can we actually demonstrate in these mechanical resonators exotic quantum states of motion of those oscillators? For example, could we create Fock states or superposition states of cat-like states? And so I've been working with Warwick on various ways that feedback control, position measurement and feedback control could prepare relatively boring quantum states, so various kinds of squeeze states in future experiments. And he's done some demonstration of the fundamental physics there, where things aren't cold enough that we're really quantum mechanical, but we've developed some feedback control approaches that allow you to get a lot of squeezing out of a device that's still coupled to a thermal environment. And so there's this, okay, so that's one sort of thing. But I mean, I could go on for, if you want me to go on for ages about that, I could. But to give you an idea, I mean, his, he's been working for a long time with these toroidal resonators that have, where they're silica resonators that have modes, high Q modes of motion coupled to high Q whispering gallery optical modes, and you can use the radiation pressure force of the optical modes to exert forces on the motion. And one thing that came out of EQUS research, some years ago now, is it's sort of hilarious. So they worked out that they could build a novel kind of magnetometer out of this. What they did is they took this thing. It's called a magnetostrictive material. It's called terphenol. So it's like it's black.
Terphenol. I've never heard of that before.
So terphenol is it's like a black goo. It's not. It's it looks like a pile of pretty much solid goo, like this black blob that he put. So he's got these beautiful, glass. You've probably seen these photos of these beautiful resonators that not just Warwick, but also people like Tobias Kippenberg in Switzerland make. And basically Warwick dropped this horrible pile of terphenol on there. And the reason to do that is that, depending on the magnetic field, it will constrict. So it's if you're familiar with piezoelectricity, where you exert an electric field and the crystal vibrates, magnetostrictive materials will respond mechanically to magnetic fields. And so by actually putting this thing that's going to tense up in a magnetic field, you can shift the mechanical resonance of these for these optomechanical systems. You can read that out optically, and actually, even in room temperature, you can actually get interesting sensitivity to magnetic fields without being. I mean, usually the competitor is going to be squids, and for certain size scales and of length scales for the magnetic field, the squids are always going to win. But these devices are actually these optomechanical devices are at a particularly interesting sort of length scale, and actually they are competitive with squids, but they don't require cryogenics. And that's almost like a and it's an unanticipated practical consequence of this work in optomechanics that Warwick's now investigating how you actually build a practical device out of that, because you can demonstrate that you've got a really high sensitivity, but there's also a long road in terms of getting something that really is a practical deployable device. But that's, I think, an example where there's really exciting physics. Can we make exotic quantum states of motion and really manipulate quantum states of large-ish mechanical systems on the one hand, and then it turns out those things are going to be great sensors in various ways that we might not anticipate fully at the moment. But an example would be these kind of magnetometers. So
what kind of application would a highly sensitive magnetometer give you? I mean, what practical problems do we really need high sensitivity to magnetic fields?
So you're going to, I mean, you and I are theorists, and you're going to stretch my expertise there. Magnetometers are pretty widely deployed. I'm trying to think. I mean, yeah, I don't want to. I mean,
you're not going to speculate.
It's surprising. So squids are the state. There are a number of. So I'm trying to think of what actually is the application. So I actually should remember what precisely is the application that's driving the interest in this particular one, but it's slipping my mind at the moment. If you look up what people use squids for, it's a surprising array of things.
Because I know also the diamond stuff that Melbourne's doing.
Yes.
So it's also related to magnetometry.
Yeah. So that's a very important. So it's a very important application of NV diamond, and there in particular, I mean, people can look at you've got these beautiful experiments people have been doing in Melbourne, but also people like Amir Yacobi at Harvard, where they can look at magnetic fields on really microscopic length scales with these sort of NV diamond magnetometers. So Amir's group has used that for really looking at magnetic impurities and almost one by one in various various magnetic materials and so on. Whereas the length scale for these optomechanical things is more like it's sort of more like centimeter scale from memory.
Because I mean, getting away from sort of the more applied side, the more technical side, and getting back onto sort of the theory of quantum mechanics and the foundational things, because some of the stuff that you've looked at is much more foundational, about this idea of technology being able to test certain fundamental principles of physics and of quantum theory. We've got I don't know if you're involved, we've got this big Bell test at the end of November that you can log onto the web and submit data to do a worldwide Bell violation. I don't know if Australia's involved in that at all. But some of the more foundational sort of achievements that either you've been involved in or that you just find extraordinary that we've been able to do with these highly engineered quantum devices.
Sorry.
Or the ones that
I zoned out. So you had me looking there for actually what one uses squids for.
That's all right. We can get back more on the theory side somewhere where you're a little bit more
So I was
comfortable.
momentarily distracted by yes. Anyway.
No, so the idea of using these devices, which are manufactured, they are engineered quantum systems, but then applying them to look at and test some of the more foundational issues of physics and quantum mechanics, things that, certainly if you go back and look at the original writings of people like Schrodinger and Heisenberg, the ideas that they thought themselves would probably never be tested.
Yeah. So, and then you're talking about work specifically we're doing in EQUS, or?
Well, no, either stuff that you're involved in that you find is interesting, or just stuff that you think is pretty cool that's going on.
Yeah. So I would say, I mean, just point out, so for example, in that optomechanical context, one thing that got me interested in the idea of feedback control for single oscillators is, and this is, something that would be nice to demonstrate one day, is, the fact that in these systems, typically what one is doing is you're making a continuous position measurement of an oscillator. So as you make the sensitivity of that measurement very high, you're necessarily heating the oscillator due to what people call back action noise, right? And so if I start doing feedback control to confine the motion of that oscillator, so suppose there's some thermal bath that's going to lead to the oscillator thermalizing at some high temperature. I want to turn on position measurement and use that to localize the atom to some much smaller length scale. I will improve the sensitivity of my position measurement, which in the case of these optomechanics experiments means turn up the laser power in order to get a better sensitivity. That will turn up the fluctuations actually in the radiation pressure force, which is this back action heating. And so what will actually happen, which wouldn't happen in a classical, that's a really simple control problem. How do I minimize the energy in an oscillator consequent on position measurement? What will actually happen in the quantum mechanical case is that as I turn up the sensitivity of the measurement, my performance will improve. And I'll be able to localize the thing better, but at some point it'll be counterproductive because there's so much back action heating that I'm going to increase the energy of the oscillator. So you might expect that there's some optimum, that you can sort of look too hard at the quantum system, and that from the point of view of a particular feedback control goal, you might not want the best measurement you could possibly design. So that sort of issue, I mean, it would be, is one that actually got me interested in feedback control of oscillators a long time ago now, but it would be something that would be interesting to see sort of clearly in an experiment. So I suppose one of my motivations in all this feedback control work is, what are things that are either practical or where we can demonstrate some of these sort of foundational sort of physics areas in real experiments. So that's sort of my interest. And you're seeing now, I think, just really beautiful work happening in circuit QED. Groups like Irfan Siddiqui's group at Berkeley, Benjamin Nouad's group in Paris, and they're just doing sort of astonishing things where they can do feedback control on single qubits, and they can really see all this quantum back action and all of those kinds of things. So that's not something that we're doing, but I think, and I should, our Roche's experiments from a few years ago, you're really beginning to see experiments where this kind of quantum feedback control is actually demonstrated in the laboratory for interesting, to really demonstrate the physics that's going on.
Right. So I mean, with the, sorry,
go ahead.
Because I was just going to mention to people, and this is what I've always found cool every time I talk to people like Warwick, because these optomechanical systems that you're playing with, they're quantum mechanical systems. They obey all the weird, spooky rules, as people like to call them, of quantum physics. But they're also quite large, aren't they? Physically, they're not single atoms.
Yeah. So it's always interesting. So this is a vexed question. So people, by the way, have done really beautiful manipulation of the states of motion of mechanical objects, and they're called ion traps, right? So there's these beautiful experiments from the mid-90s, around about the time I started my PhD, actually, in Dave Wineland's group, where they can make a Fock state, and they can build various superposition states, and they could do tomography on those things. And there's actually, experimental reconstructions of Wigner functions of exotic quantum mechanical states of motion of a single atom, effectively. And so the argument you might make for optomechanics is, I want to produce exotic states of motion of things that are not one atom.
Yeah. And
I think it's really reasonable to argue that so there's a vexed issue about the quantum mechanics the wave function of the oscillator doesn't care about how your thought, it doesn't know how classical you think that oscillator should be.
Yeah.
Right? So somehow or other, I think it's more surprising to me and to many people if you can do that sort of manipulation with something that is more massive than a single atom.
Because the examples that I always remember when I was younger was, Zeilinger's effort to do two-slit experiments with successively larger and larger objects.
Yes.
I think he proposed at some I think he proposed at some stage they wanted to try and do it with a virus. I don't know whatever happened to that idea.
I think it's probably hard.
Yeah, I think so. But these optomechanical systems are another good example of otherwise large objects.
I think the one thing that you want that is often so there are so it just because it's a vibration of a reasonably large object. So, for example, Warwick's toroids. That doesn't mean, for example, the motion that is being detected is large. So, if you just said, what is the so having made the oscillator, the natural length scale, of course, is the RMS size of the ground state wave function.
Yeah.
And if you were to compare the RMS size of the ground state wave function in some of these mechanical experiments with, say, the ion trap experiments, I think you would find actually maybe the ion trap experiments are bigger.
Right.
But certainly there would be, it wouldn't be clear that, it's more macroscopic. The object is macroscopic, but there are vibrations that are actually pretty small.
Yeah.
That are what is being, the mechanical states that are being manipulated are not, they're not large translations of anything. They're typically, some vibration of a large object, but those vibrations are themselves, their characteristic length scales rather short.
Yeah, I remember seeing the pictures.
And also the effective mass may be not nearly as big as you would think. You might look at the thing and say, well, it's quite a heavy thing, but often that, it is possible to, whereas when you look at the continuum mechanics of the vibrations of that, you can actually work out what's the effective mass, like how much mass is really moving in these vibrations. And those effective masses are also not necessarily so great, although they're certainly in excess of a single atom. And the question of really, what should I regard as a big superposition, or what should I regard as, what is, quantitatively, what kind of experiment am I trying to do that's going to be a really vivid demonstration of the fact that these mechanical objects are quantum mechanical and I can produce superposition states or Fock states. I think it's quite controversial. You'll find, particularly for superposition states, you will find all kinds of literature about the size of a superposition, which is obviously not, am I talking about the superposition of a lot of atoms? Am I talking about the superposition of a lot of mass? Am I talking about various quantitative ways in which you can make certain superpositions larger than other ones? That's actually a very vexed issue. It's very hard to work out exactly what you should mean by that. There's an intuitive notion that it's more surprising if I superpose a lot of stuff over a large distance, but exactly how you should quantify that turns out to be surprisingly controversial if you go look in the literature.
I mean, do you have a position on this? Do you have a favorite? No. You are completely on the fence in this so far.
No. I mean, one person who's worked on that is Tony Leggett, but there are a number of views. Yeah.
But I mean, the technology itself, the stuff that's actually being designed, does that help inform any of these decisions or help push theorists in the right direction? Or is it really sort of more of a technological thing?
Yeah, you're saying...
I mean, is there anything the experiments themselves can tell you to help sort of clean up these controversies? Or is it still very much in the theory domain?
Yeah, I think those things tend to be in the theory domain. And then there's a sort of a... then there's also, so I think these discussions do inform people in thinking about, what would they find interesting? What is the interesting, from the point of view of demonstrating some fundamental physics, doing some of these fundamental experiments that date back, to thought experiments in the foundation of quantum mechanics. The question of what would be a more interesting demonstration, or are the demonstrations in optomechanics qualitatively distinct from the much earlier demonstrations in ion traps? That's, I think, something where people bring some of their ideas about this and then argue about it, perhaps over beer, as to which, I do think it is kind of that is perhaps a bit of a theorist discussion, but I think it just sort of is somehow clear that's a really interesting thing about this field of optomechanics, is the idea of sort of really pushing our ability to control increasingly, at least mesoscopic objects, quantum mechanically.
So pushing back onto sort of a broader sense about EQUS and about the specific work that EQUS does, a lot of the people that have done the podcast who are very much ostensibly coming from the quantum computing side have noticed and have said the push now that the quantum computing and sort of these, I don't want to say traditional quantum technologies, maybe more well-known quantum technologies, is now moving towards industrial interest. There's a lot of money and a lot of people coming in. The CQCT in Australia now has investment from Telstra and the CBA. In terms of sort of EQUS's role within this sort of jungle and engineered quantum systems, are you seeing the same kind of private interest, or is it still very much in the academic physics lab camp at this point?
So, one thing that I would say is, the field has changed, I think, in the last 5 years or so quite dramatically in terms of the level of interest, both from government and from industry. And as you're saying, a lot of that interest relates to quantum computing, but not all of that. And at Sydney we do quantum computing, and particularly colleagues of mine like David Riley are involved in. In fact, all of us really work on quantum computing to some extent. So what I would say is but if you, for example, look at the roadmap that's been set up in the UK for quantum technologies research, they are actually emphasizing a range of applications, and these could be quite specialized things, like what can quantum physics do for the precision of atomic clocks? That's something that's completely certainly a quantum technology. It's a practical application. Not everyone's going to have a quantum atomic clock in their pocket or anything, but
not yet anyway. You never know what Apple's going to do with the iPhone 10 or something.
So in these applications that look like metrology and sensing, there could actually be shorter term applications. And I think if you look at the quantum technology hubs in the UK, there's actually is an emphasis similar to our centres that's quite broad, and particularly on applications where quantum computing is actually somehow a long-term technological goal that is going to require investment by large industrial partners or governments or whatever. So I think. And so in those quantum technology hubs, you see increasing collaboration between academic researchers and industry on the full range of possible applications of quantum technology, and that's something we really want to build in Australia in the new centre. But then, as you say, there's major tech companies who've gotten interested in quantum computing in the last little while. Google, IBM, Microsoft. So Microsoft is a partner of ours in our centre, and particularly they collaborate with Dave Riley's group here at Sydney.
Yeah, he's part of Station Q, isn't he?
Yeah, so there's a Station Q. So there's this Station Q effort of Microsoft, which has a Sydney version, so Station Q Sydney, which is and there's that involves Delft and Copenhagen, so the Coenhoven and Marcus groups. So those are people who are working particularly on semiconductor devices, maybe quite exotic semiconductor devices for quantum computing.
So with the Australian context and EQUS, I mean, are there industrial people that are interested in the same way that CBA and Telstra is interested in quantum computing?
So I think if you look, I mean, it's sort of interesting, the Australian environment. So there are some, quite small, technical startup companies. So, for example, Mog Labs, which is a technical company that's run by Rob Sholton, and that's an EQUS partner. So Mike Biersek's worked with Rob's company on light sources that are actually great for his ion trap experiments, but also for other people's ion trap experiments. There's one of the new members of EQUS is a guy called Daniel Shattuck at ANU. So here's a company called Liquid Instruments that's doing some really exciting things to do with sort of programmable FPGA control. And their sort of point of difference is that their instrument can be controlled entirely through an iPad app, and it's very reprogrammable. So they can actually sell you new functionality for your same device as they develop the software for it. So they're building standard signal microwave control function generators, these kinds of things, using FPGAs through this app kind of thing. So that's something that's grown out of Dan's technology. Actually, so that's one of his efforts. It's not really part of EQUS per se, but it's just an example of like a small business that's building something high tech that might have educational applications as well as scientific research applications. And Mog Labs is a similar sort of, they're basically selling to research around the world. So there are a number of these sort of small startup type companies. Then, as you say, if you go and look at, what are major companies in Australia? Well, the banks are major companies, and you've seen them investing in quantum computing. But there's a big difference. I mean, the big, global tech companies like IBM, Google, and Microsoft that are getting involved in quantum technologies, they have in-house technical expertise. They're, whether that's on both the theory side and the experimental side, and they're hiring large numbers of, really excellent people to do research, and they're companies that have already, existing environments of PhD scientists and engineers, large numbers of them. That's not what these, Australian banks don't employ a lot of people that use dilution fridges in their daily work, and so it's really great that those companies have gotten interested in quantum computing. But I think that at the moment, I don't see them having an interest in some of these other, like, you would be pretty, if you say, oh, you want to build an atomic clock, or do you want to see if we can turn an idea for magnetometry that might be a device that's interesting down a mine one day, or something that's going to be good for navigation, or something that's going to change magnetic resonance imaging, that tend to be the sort of application areas people have in mind. These are not the companies that are going to want to build that product. So whereas I think they can see, if you had future quantum technologies that maybe problems you could solve on those quantum computers might have an impact on their business, and then they're really excited by the idea that there's world-leading research in Australia, that's an appeal for the banks. And I'm not sure at the moment that there are big companies like that in Australia that are interested in some of these other application areas. But we'll see. I mean, I think it's early days.
Well, you can only hope.
That's not an actual, yeah, exactly.
Yeah, no, I mean, all these kind of things always start off in academia and then slowly push into the outside. It's just more of the sort of where you are in comparison to where people see quantum computing is, because certainly quantum computing is the thing that you see or people see on the newspaper every day.
Yeah, I think that's right. I mean, in Australia, certainly, and you know, there's really great people working on quantum computing here, so that's good reason for it.
So we're basically buffering up against our 45 minutes here. The last thing that I generally like to ask everyone who comes on is to be a bit of a fortune teller and to either speculate or at least offer your hopes as to where you think the tech is and where you think the research will be in the next 5-ish so years. If you want to make a commitment, some people just say, I don't want to predict anything.
Okay, so for some context, so I have been saying, so I've never been an optimist about quantum. So let's talk about quantum computing to begin with. I've never been an optimist about quantum computing. I would have told you when I was a PhD student that I thought it was 50 years in the future, and I think until quite recently I would have said the same thing, even though my PhD is now 20 years ago. So I've always felt that the technical challenges are really demanding. But I do think, and we've been talking about the way the field has changed and the fact that there are some really heavy duty, you know, people like IBM are able to muster really large numbers of really good people with experience in the field to focus on building quantum computers. And, you know, you've got 30 PhDs or whatever they have now working on those experiments. Yeah. And so you see something which is a 5-qubit device, which can be operated by high school kids, you know, programmed, and it's robust enough that it's running pretty much all the time. I think that reflects, you know, the really rapid development of circuit QED, and people like Rob Sholkoff and Michel Devray and have really, and Steve Gervin on the theory side have really, you know, created this amazing experimental system, which you can really have a lot of hope about building quite large devices in a reasonable number of years. A number of years is not 50. I think that you know, we'll have 100-qubit devices in 10 years, I think. So I think that's really exciting. So that would be one thing that I think you can actually envisage, let's say 100-qubit devices on, let's say, a 10-year timescale. I think that is a realistic expectation for circuit QED and maybe for certain other, maybe for ion traps and semiconductor devices as well. I'm not sure. I think that if the model for doing work in the field turns out to be that you need 30 PhDs with the resources of a major international tech company, that there will be experiments and actually there will be theoretical work. I mean, if you look at Microsoft's theoretical activities, there will be things that we in academia shouldn't be doing, or you know, so I would be asking myself 5 years from now, like, what am I doing that's really distinctive research in quantum physics that, you know, isn't competing with vast, well-funded research efforts in quantum computing? So I think, you know, it behooves us to be more creative, to be more long-term, to be training really great people that are going to do this, but we're not going to build quantum computers in universities, I don't think.
No.
So I think that there will be a real search for new ideas, and I really hope someone has a bright idea about what to do with a 100-qubit device, because at the moment I don't think we know what a 100-qubit device is good for. So that's
nothing
something
practical in my opinion.
Yeah, exactly. And maybe if you put enough resources, you're just going to wear that, and you're just going to keep on pushing until you get you know, much bigger devices. But it would be great if a 100-qubit device was good for something.
Well, I think if you had low enough error rates, it would be.
If you had low enough error rates, I mean, you could do some interesting things, and certainly in quantum chemistry simulations, that's pretty clear. But in lots of other places, probably. But at the moment, these things are going to need error correction, and error correction overheads are more than 100. So, so in theory, actually, by the way, I really hope that we have schemes for fault-tolerant quantum computing where the overhead is not, I don't know what number you would want to give it, but the number is huge.
Well, depending on optimization,
depending on the size,
by 10,000 at this point.
Yeah, and it depends on how big a computation you're talking about and so on. But the point is, yeah, 10,000 is like a good. I can agree that I've seen multiple places where that seems like that's a robust number of something you can find in the literature, right? And it seems to me that if that number is not 100, then the whole field is dead. I think it's got to be 100, and so
that's really optimistic.
I think that. Certainly, if you want to build a device, something that's going to do Shor's algorithm factoring, if the overhead's not 100, then I think there's a problem. So I think there's a big call for theory for reduced overhead, and I'm also really excited at the moment by connections between ideas from condensed matter physics, often quite exotic ideas from condensed matter physics, and things that might have application in quantum technologies, but specifically in fault-tolerant quantum computing. So here we've been working on connections between something in condensed matter physics called symmetry-protected topological order and something in quantum computing called measurement-based quantum computing. Actually, this is a great result by Rausendorf, building on some of the work we were doing, that really shows that's a really deep connection. It's kind of fascinating. I don't think it's well understood. I think there are many of these constructions that we have. Another one would be surface code-based fault-tolerant quantum computing, where we don't completely understand how that works. I mean, we understand how it works, but if you had to come up with another way of doing, are there families of analogous schemes? Can I build schemes for fault-tolerant quantum computing where the underlying code has different kinds of anyons in it than the anyons in the Kitaev surface code? There are a lot of natural questions there about what is the general structure of that whole edifice, and is it possible to actually create families? And the motivation for creating those families would be, maybe we can reduce the overhead if we have quite a different scheme. But in order to do that, we'd need to have ways of generating new schemes for fault-tolerant quantum computing. So I would hope that in 5 years, actually, we've seen first in this field dramatic reductions in the fault tolerance threshold, dramatic increases from 10 to the -5 or 10 to the -7 to 10 to the -2 in favorable cases. And then I think now you're seeing a lot of research on various ways to reduce the overhead. And that has also been going down by orders of magnitude as people have thought about different components of what's going on. But I think there's still a lot of call for a major advance there. I would actually hope as well that at some point people work out with all these ideas about many-body states, exotic many-body states like surface code states, states with topological order, things like this. Are there applications of that are not quantum computing? Like some of these other things, like different kinds of sensing, and so some of these, are there applications of that sort of thing to sensing, to metrology, this kind of thing, because that might be an avenue towards a use for 100-qubit devices. So you can make.
I would agree with that.
So with a 100-qubit device, you can make something that's really a beautiful example of a surface code. Is there some application of that that's more maybe niche, but as I say, some sensing or imaging metrology, something like that?
It is an actual application rather than just...
That is an actual application. That's actually, good for something. Yeah.
Well, wonderful. So before we close things off, I always love to give people a chance to plug anything interesting going on at Sydney or Australia in general that you want to point out.
Oh, Well, I'm on the steering committee of QIP, which is the premier quantum information theory conference.
Yes.
And it's actually, if you're listening to this, you've just missed the early registration deadline and also the poster deadline, but everyone should go to QIP. And we've it's in Seattle this year. And
sunny Seattle.
Sunny Seattle. And so that should be a great event early next year. That's probably I'm sure there are, and yeah, people should come visit us in Sydney, but I don't have anything specific to plug. No
problem. Well, as usual, I'll put the links both to the Sydney Physics website and to EQUS below for anyone who wants to check it out or get into contact with anyone to do work or just ask questions.
Oh, I do have a plug. My
Yes.
colleagues will kill me. We have an open ad for postdocs at the moment. And so we actually have a number of possible postdoc jobs. So when you find that website, you'll actually find that there is a job opening if you're interested in quantum theory.
Yes. So I'll put that as well below. And yeah, there's more than one available, right?
Yeah. So the ads, I believe that we will certainly appoint at least 2 people.
Okay, wonderful.
But there may actually be. The thing about getting a lot of money from the government is it gives us the opportunity to grow the group, and for various reasons there may be, so if you're interested in quantum physics and might want to live in Sydney, have a look at that ad and
apply. No, I would definitely recommend it. Sydney has exploded now with quantum research in all facets of quantum. All 4 universities have now got major efforts, so it's extremely good to be in Sydney at this time. It's very good to be in Australia too, considering what unnamed things are happening in the rest of the world.
Right, yes.
Anyway, so thanks again, Andrew, for sitting down for an hour or so and having a chat. And hopefully chat with somebody else from EQUS in a podcast in the future.
Excellent, yeah.
Great, and thanks everyone again
Thanks very much.
tuning in. This should be uploaded to all of our podcast accounts within the next hour. So thanks again, and stay tuned to our social media accounts when we book our next guest. So thanks.